Hey everybody, welcome to lecture 4. First, exponential functions. So an exponential function has this general form. It's y equals a to the x, where a is a positive number. It's actually kind of fun to play around with the case where a is not a positive number. If, for example, you had the function y equals negative 2 to the x, like graph that in decimals or somewhere, it's a crazy function. It's never equal to 0, but it goes from positive to negative all the time. Its continuity is a mess. The function is just crazy. And so in order to avoid the insanity in this function, an exponential function only has a positive base. And to get a quick glimpse at why this thing is so crazy, think about two values of x that are really close to each other. Let's think about, like, I don't know, we'll say 2/3, and we'll think about something close to that 3/5, right? So that's like 0.66666, that's 0.6. They're pretty close to each other. Negative 2 to the 2/3, well, since you raise it to the second power and then cube root it, it's positive. So this gives you a positive answer when x is 2/3. When x is 3/5, everything's odd. So negative 2 to the 3/5 power is negative. Because when you raise a negative to an even, it goes positive, negative to the odd stay negative. So real fast it went from positive to a negative in between 0.6 and 0.66666, but it never equals 0. This function will never equal 0. And you can even make it even stranger. Let's say that you throw a, I don't know, let's put 5/6 in there, which is 0.83. Negative 2 to the 5th power is negative 32. The 6th root of that, well, that's complex. We have now left the real numbers entirely. So these fractions are all relatively close to each other, and we have a positive, a negative, and a non-existent. And you can pick three numbers in any interval, doesn't matter how small the interval is, and you can find three numbers that give you a positive, a negative, and a point where the function does not exist amongst the real numbers. As I said, this function's crazy. It's a complete mess. So exponential functions have a positive base, because positive bases don't have those issues. They don't have sign switches and an infinitely small interval. They don't have discontinuities. They're all good to go. Some basic properties of the exponential functions are listed here. When you multiply terms with the same base, you add their exponents. When you divide terms with the same base, you subtract. A negative exponent is 1/a to the m. A to the 0th is 1. These are all pretty easy to prove as long as m and n are integers. They're true for any real numbers. M and n are real numbers. But it's actually really hard to prove it for real numbers. It's actually really hard to prove this for rational numbers. But as long as you have whole numbers, whole positive numbers, this is pretty easy to prove. Not that we are going to concern ourselves with the proof. What we are going to do is concern ourselves with the derivative of an exponential function. So the derivative of y equals a to the x. Let's try to derive this with the limit definition of derivatives and see how far it takes us. So the derivative with respect to x of a to the x is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, where f of x is a to the x. We then use this property right here to rewrite our first term. The rest of the limit stays as it is. Right? We just rewrote a to the x plus delta x. And now we have these two a to the x's. We can factor them out. And for this limit, delta x is the change in quantity, which means a to the x in the context of this limit is constant. And so we can factor a to the x outside of the limit, giving us a to the x times the limit as delta x goes to 0 of a to the delta x minus 1 over delta x. This is actually pretty interesting because we just showed that the derivative of a to the x is itself times this number right here. And this is a constant. And we know this is a constant value because there are no x terms in there, right? All the x's we factored out. So this limit is a to the x times some number. And that number is dependent on a. So it's a constant that depends on a. We know it depends on a because in this expression, the only thing that we can change is a, right? 1's a constant, and delta x is going towards 0. A is the only changeable quantity. So the value of this number will change as you change a. So the question becomes, for what value a is this number equal to 1? Because if this constant equaled 1 for that base a, it would mean for that base a, the derivative of a to the x was just itself times 1. Just to kind of like write that in some easy to see terms. The derivative of a to the x equals a to the x times some number that depends on a. And so the question is, what value of a gives us 1 for that number? And there's a few ways to find the answer. One way is called linear interpolation, which is a fancy word. Linear interpolation. It basically means you just guess the value of a, and if it gives you too big of an answer, like that's over 1, you guess a smaller value of a, and if that one's still too big, you guess smaller. If it's too small, you guess bigger. And you pretty much just kind of like hone your answer. There's more of a process to it than I'm saying, but it's like a organized guess and check. And gradually you find the value of a that gives you exactly 1 for this constant. And it turns out that that number is 2.71828, 4590, 4523, ... which we know as e, which is pretty cool. We just figured out that the derivative of any exponential function is itself times some constant. And we also figured out that if that a to the x was e to the x, that differentiates to itself. We just showed the derivative of e to the x is e to the x. This is the only function whose derivative is itself. It differentiates to itself, which is kind of cool. Like for example, at the point x equals 2, the y value is e squared, and the slope is e squared. The slope is always the exact same as the y value. There's a bunch of cool things about e. I can go on and on and on about e. I will allow myself a few minutes to discuss the awesomeness that is e. First of all, this fun little thing right here. This is the only number that I know so many decimals to. To this cool trick that someone showed me, that Andrew Jackson was the 7th president. I know, stay with me. He was elected in 1828, served 2 terms, then 45, 90, 45 triangle. 23 is my own contribution. That's from Michael Jordan. That was his number. And so it's a pretty easy way to memorize all those digits of E's decimal approximation. But back to E, just a short glimpse of E. A few cool things about it. One is that we haven't mentioned this function yet, the natural log function, but this function, natural log, predates E by decades. By like 40 years. Which is crazy, because you learn that log x is a base E logarithm, but actually log x came first, right? E actually came afterwards. E was discovered by one of the Bernoullis. There's a few of those members of that family that do a bunch of awesome things. He was trying to figure out essentially what is the most money you can make if you invest $1 at 100% interest for 1 year. Because the more that you compound your interest, the more money you make. For example, if you only compound your interest once, at the end of the year, you make $2. You make the original $1 plus the 100% interest, which is $1 more. So I should say you have overall $2. And he figured out that if you just compound your interest more and more and more, the max amount of money you'll have is E, that 2.71828 blah 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 dollars. But this number appears all over the place. Like, it really is only possible to define this number with the aid of calculus. We'll prove later on this summer that this limit gives you E. This is essentially Bernoulli's problem written in calculus formation. This gives you the amount of money made if you invest $1 at 100% interest for 1 year. You could also express E in terms of sums. E is the sum of 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial all the way to infinity, which is kind of cool. Oops. But again, that's calculus. You have to use calculus to define E. And E appears all over the place. Like E appears in probability. There's a famous question in probability called the hat check problem, which harkens back to the days when gentlemen wore hats on a regular basis. We don't do that. So pretty much what this problem is, it's just a problem, is like consider graduation. And there's like 2,000 students who are graduating. And for some reason, the school decides to hand out the diplomas at random. Like they just give out each diploma at random to a random person. The odds, or sorry, I should say the probability that no one gets their diploma back properly is 1 over E. And there's a whole class of questions in probability whose probability ends up being 1 over E. The larger the graduating class is, the closer the probability is to exactly 1 over E. So E pops up in probability. It pops up in stats. Those of you who have taken stats know the normal distribution model. Normal distribution, that little bell curve thing. The equation for this curve is an exponential function with base E. I actually forget the expression. I haven't had to use this thing in so long. It's like something like this, but it's not quite this. Actually, it might be this. I don't even know. That might be it. But anyways, this is an exponential function with base E. So E pops up in probability, pops up in calculus because it's the only function whose derivative is itself, pops up in stats, it pops up in trig because if you throw some complex numbers into the exponents, all of a sudden E becomes a trig function. Pretty much this thing just pops up all over the place. This, by the way, that's called Euler's formula. It leads to Euler's identity. Euler is a mathematician from the 1700s, a whole bunch of awesome stories about that guy. But his identity is that e to the I times pi plus 1 equals 0. This simple, elegant equation is able to relate pretty much the 5 main constants in math: 0, 1, e, I, and pi. Just a nice, clean expression that comes right from that formula right there. So we'll stop our talk about E there, although we could go on because there's a whole bunch of cool stuff about E. But for us, the important thing is that, where is it? Hold on. There it is. The derivative of e to the x is e to the x.